Okay. And that's it. Any questions on overview of conduction, convection, or radiation? No? Have you guys seen all this content before? No? Okay. As we're switching to the next packet, just for my own curiosity, does this feel like something you would want to see like again in a subsequent class? Like, is it hard enough that you'd want to have it reiterated? Yeah, maybe. Okay. Because we do heat transfer in 3500 too, and I feel like there's a lot of repetition. Yeah.
Where is Celsius?
Oh, I just converted back to Celsius in the end. Sorry. Okay. I'm going to open up. Okay. So this topic is a deep dive on conduction only. And in it, we are going to specifically focus on problems that are one-dimensional. And in particular, what we're going to be looking for instead of finding rates of heat transfer, so instead of finding Q dot, is we want to find the resulting temperature distribution and the resulting rate of heat transfer. So we're still, still Q dot, but mostly the new thing that we're adding here is the temperature distribution of our solid body that's undergoing conduction. Okay, so just to remind you, Fourier's law of conduction for a 1D problem in the x direction looks like the following. So we have Q dot x is equal to minus Ka dt dx. Okay, so if you remember in general, we had Q dot x is equal to minus Ka partial t partial x. Q dot y is minus Ka partial t partial y. And then Q dot z is equal to minus Ka partial t partial z. All right, so these are the equations in each of the three directions. Because we're saying that this is a one-dimensional problem, you might notice that instead of having a partial derivative, I have a total derivative, right? So the partial derivatives in here are because temperature is generally a function of x, y, and z. So when you have more variables in your, more dependencies in your variable t, it has to be a partial derivative. But now that we're saying temperature only depends on x, I can write this as a total derivative. Okay? Okay. Also a reminder, area is the cross-sectional area that is perpendicular to x. So this is the YZ plane. All right, so this is the x direction, and then this would be your area. Okay. Da, 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 da. Y, Z. Okay. And so we're initially going to focus on steady heat transfer problems, which we all know means that the time derivatives are 0, right? Okay, so if we look at 1D conduction through a plane wall, and we want to know the steady temperature distribution in that wall that has a thickness L and a thermal conductivity K, and then we're going to assume it's 1D in the X direction. What we have is the following. So we have our little slab here This is our x direction here. All right, and then our thickness in that x direction is L. And we're going to have q dot conduction in the x direction. So you can see that here. So here's our q dot conduction. This is in the x direction. And we have on either side of our wall, so on the back side, we have T1. And then on the right-hand side, we have T2. All right, and so to do the analysis for this problem, we're going to take a little infinitesimal skinny slice of this wall of thickness dx, and we're going to place it between some arbitrary location x and x plus dx. All right, so essentially what I have here is I want to take this little slab all right, so here we have x and then x plus dx. And then this face right here is A. And we have on this side q dot x. And over here is q dot x plus dx. Okay. All right, so since we want to find t of x, and there's no mass flow in this system, we're going to use, oh no, okay. Uh, would this be an open or closed system? No one? Yeah, it's closed. So there's no mass flow. We're just looking at like a slab of solid material. So this is just a closed system. So I can write down conservation of energy for this. So I have dE dt is equal to q dot minus w dot, or q dot in minus q dot out minus w dot in minus w dot out, right? And we know that this is steady. So since it's steady, we're going to get rid of our time derivative. And there's also no work done on it, right? Okay, so this just means that we have q dot in minus q dot out is equal to 0. Or we could write this as q dot in is q dot x. That's our left-hand side incoming rate of heat transfer minus q dot x plus dx is equal to 0. So I can rewrite this term in the following way. Does anybody know where this comes from? I'll be so impressed. It's okay if you don't. So this comes from a Taylor series expansion, uh, which hopefully you all just very much love. So just to remind you, the Taylor series expansion. So if I have some function f and I know its value at a location x, but I want to predict it at a new location dx away. So I can approximate f at x plus dx as the following. So I can say, well, it's equal to the value of f at x plus the derivative of f with respect to x times dx plus 1 over 2 second derivative of f with respect to x dx squared, and so on and so forth. So this is just a truncated version of this to predict what q dot at x plus dx is based on what q dot at x is. Okay? Okay, awesome. All right, so I can plug this in and get everything in terms of q dot x, right? So I can say, all right, great. So I have q dot x minus q dot x plus d q dot x dx times dx, and that whole thing is equal to 0. So we'll notice that we have a q dot x minus q dot x. And this whole thing then becomes minus dq dot x dx, oops, times dx is equal to 0, right? Dx is a little tiny sliver of space, but it is not 0, right? So I can divide through by dx here, and I can just say that dq dot dx is equal to 0. So what does that mean about q dot x? It's not necessarily 0, but it is a constant though, right? So it's not changing with respect to x. So that means the following. So since dq dot x dx is equal to 0, q dot x must be a constant. Okay. This is interesting and useful, but it does not give us a temperature distribution, however. All right. So now let's introduce Fourier's law of convection, or conduction, sorry. All right, so we have that q dot x is equal to minus k a dt dx. All right, so I'm going to put this whole thing into here. So I have that the dx derivative of minus k a dt dx is equal to 0. K is a material property. It should not change with X because we have this uniform slab of material. We also have a uniform slab of material, so A will also not change as we move in X, right? So I can pull both of those things out of my derivative. So I have minus Ka ddx of dt dx is equal to 0, right? And K and A are both non-zero values that I can divide through on both sides. So that means that I have the second derivative of temperature with respect to X is equal to 0. All right, so now what we have is an ordinary differential equation in terms of T. All right. So anytime you have a differential equation, the number of derivatives that you have in space, that is the number of boundary conditions that you need. So you're going to end up with constants of integration when you solve this, two of them to be precise. And so you need to know two temperatures at two physical places in space in order to solve this equation. If we had a time derivative, we would also need to know a value of the temperature at some point in time as well. But this is steady, so don't worry about that. But I wanted to mention. Okay, so anytime the number of derivatives that you have in space are the number of boundary conditions you need. The number of derivatives that you have in time are the number of initial conditions that you would need or time conditions that you would need. Okay. Okay, so we need two boundary conditions to solve this. And fortunately, we have them. So we have the temperature at x equals 0 is T1, that's known. And we have the temperature at x equals L is T2, and both of these things are known. Okay, so what I'm going to do is I am going to do separation of variables and I'm going to integrate it, and I'm going to do that 2 times. Okay, so we're going to solve this in 2 steps using separation of variables and integration. All right, this is a pretty friendly differential equation, but I'm going to write it out like this. Okay, so for my first step, I am going to treat dt dx inside of those parentheses like it's its own variable. All right, so I essentially have the derivative of a thing with respect to x is equal to 0. So when I separate my variables, it's going to look like this. I have the differential of dt dx is equal to 0 times dx, and I'm going to integrate both sides. What is my integral of my left-hand side? Don't panic. So this is the same thing as if I had the integral of dy, I would just get y, right? So my integral of dt dx is just dt dx, okay? So I keep this around. And then if I integrate 0, I get a constant, right? So I just have a constant. All right, so this is just another way of writing kind of something that of writing what we've said before, where if the derivative of something is 0, that means that something must be a constant. All right, so it's just another way of looking at it. I am going to do this same thing a second time. So we will repeat this. So I'm again going to separate my variables. So I have dt on one side, and I have c1 times dx on the other. So I have my t's on one side, my x's on the other, and I'm going to integrate this. All right, integral of dt is just t. And then my integral of c1 is c1 times x plus another constant of integration. Okay, so this is where my 2 boundary conditions come in because I have a C1 and a C2 that I need to sort out. And so I will apply them now. So first, I want to use that T equals T1 at x equals 0. So I have T1 is equal to C1 times 0 plus C2, which means that C2 is equal to T1. Oops. All right, and then I'm going to apply my second boundary condition, which is T is equal to T2 at x equals L. So I have T1 is equal to T2, which is equal to C1 times x. We're substituting in L. And then C2 we already found was T1. So I'm just going to solve this for C1 now. So I have C1 is equal to T2 minus T1 divided by L. All right, so I can put this into here. And then my final solution then is temperature is equal to T2 minus T1 over L times X plus T1. Any questions on how we got there? Oh my. Do we feel okay with the separation of variables and the integrating twice? Okay. Okay, one last thing I want to say about this and then we will be done. Which is, if you remember Fourier's law of conduction. No. We'll make it, I swear. So Fourier's law of conduction, if you remember, says that Q dot X is equal to minus K A dt dx. And I can plug in what dt dx is now. So I can take an x derivative of this thing. And I find that I get minus Ka times the slope. So T2 minus T1 over L. And if you remember, this was our original conduction heat transfer equation. Remember? Yay. Okay, that's all before my iPad yells at me again. Any questions? No? Okay, awesome. Have a good weekend. I will see you all on Tuesday. Keep an eye out for the practice exam tonight. And so now we're going to talk about an analogy approach to looking at these types of systems, which is known as the thermal resistance concept. Okay, so we already just derived the 1D conduction heat transfer equation for the rate of heat transfer through a plane. So it looks like this. And we are essentially going to say, well, what if this is actually a temperature difference divided by some thermal resistance Rk, where, of course, if you compare the left and the right-hand side, you see that Rk must be L over K times A. Okay. Okay, so what we're going to do is we're going to consider an electrical current flow through a resistor as a result of a voltage potential. So we're going to call this voltage potential V1 minus V2. And then we're going to recall Ohm's law for an electrical circuit, which is the following. So we have I is equal to V1 minus V2 over R. And I'll call this RE because this is electrical resistance. All right, so just to draw this, so we have our voltage 1 here, our voltage 2 here, and our electrical resistance here. And so we have current going in this direction, I, which is V1 minus V2 divided by RE. Right? Okay, so if we compare this Ohm's law equation with our 1D conduction equation, we can see an analogy between the diffusion of heat and that of an electrical charge. And so just like electrical resistance is associated with the conduction of electricity, thermal resistance is also associated with the conduction of heat. And so with this analogy, we have that Q dot is essentially the equivalent to electrical current I, which I guess I didn't write down. So this is electrical current. Okay. And then the temperature difference, so T1 minus T2 is analogous to the voltage potential. Okay. Okay, so all right, so we can draw analogous electrical circuits between any two temperatures that derive a temperature potential. So we can say if we have some thickness of material with Q dot going in this direction, if we have T1 over here and T2 over here, this is our length. We can also write this in the following way. Where Q dot is just T1 minus T2 divided by RK. All right. Okay, so just in the same way that we could draw a circuit for conduction, we can also do this for convection. So if you remember, we have our convection equation shown here. Okay, and so we can write this differently. So if I wanted to put HA into a denominator, I would just call it 1 over HA. So these are equivalent. And that allows us to have a convective thermal resistance, which is the following. So we have Ts minus T infinity over Rc. Okay, so Rc is our convective thermal resistance, and it's equal to 1 over H times A. Okay, so again, this is not enthalpy. This is our convective heat transfer coefficient. All right, and then A is our area that is exposed to the fluid where the heat transfer is happening. Okay. All right, so if we were to draw kind of this exact same scenario here, where we have our solid exposed to convection. So we have Q dot convection going out this way, and we have our ambient temperature out here, our area, as well as our surface temperature, Ts. This is the same thing as writing our circuit like so. So we have T infinity over here, and then our surface temperature here. And then this is our C, where our Q dot for convection is Ts minus T infinity divided by RC. Again, RC is just this 1 over HA. Okay? In the exact same way, we can do this for radiation too. Okay? So our radiation equation looks like this. We have a small problem though now because we have T to the fourth power of our surface minus T to the fourth power of our surroundings. If you remember, we want to have a TS minus T surroundings. So we're going to do a bit of algebra to get that to happen for us. And then we'll get a factor of TS minus T surroundings at the end here. And then everything else will get lumped into that resistance. Okay. So when we do some algebra, to isolate a factor of Ts minus T surroundings, what we get is that Q dot for radiation is equal to epsilon times sigma times the area times Ts squared plus T surroundings squared times Ts squared minus T surroundings squared. All right, so I've just decomposed my Ts to the fourth minus T surroundings to the fourth into these two factors. And then I'm going to decompose that second one, factor out that second one more time. So this is broken down into this. And then I'm also going to, oops. I'm also going to factor this one as well. All right, and so when I do that, I get epsilon theta A Ts squared plus T surroundings squared times Ts plus T surroundings times Ts minus T surroundings. All right, so this guy is that highlighted portion now. Okay, but you'll notice that now we have this factor we were looking for. So we wanted to break this out. Which means everything else, all the rest of this, is 1 over our thermal resistance for radiation. Okay? And I will note here that the standard kind of practice, so we define a radiation coefficient, HRAD, is equal to epsilon times sigma Ts squared plus T surroundings squared times Ts plus T surroundings. So we get that Q dot rad is HRAD times A Ts minus T sur. All right, so now we have our heat flux due to radiation. That's basically the same shape as what we're seeing for conduction and convection. All right, and so this means that we can rewrite this as Ts minus T surroundings divided by 1 over HRAD A, where this is our rad. Okay, so our rad is 1 over HRAD times A. All right, so very similar to what we had for convection. All right, so if I draw this as a mechanical system as well as a electrical equivalent. So if we have some little object right here and it is losing heat due to radiation. So we have T surroundings, so temperature of our surroundings. And then on this material, we have epsilon, we have A, and then we have TS. We have our same Q dot rad equation that we would always have. And then if we wanted to write this as a thermal system, we would just have TS, T surroundings, and then this resistance is R rad, so our thermal resistance due to radiation. And Q dot for radiation is equal to our TS minus T surroundings divided by R rad. Okay. All right. Okay, so now that we have the framework for analyzing thermal systems as circuits, we can also extend this to thermal networks. Okay, so if uh, if we want to do a more complicated problem, we can use our rules from circuitry to help us out. Okay, so what we're going to do is we are going to look at a plain wall, but we're going to assume that this wall has a thickness L and conductivity K, and it's going to separate two fluids of known temperature. And we're going to also assume that we have our convection heat transfer coefficients on both sides are known to us. Okay, so we have this thickness L, and there's a given K value for our material. And we know that we have heat transfer going this way. This should really be drawn in 2 dimensions because this area here is where we're doing convection. And then same on the back side, but it's kind of not visible. Okay, so what we have here is on this side, we're doing convection. In the wall, it's conduction. And then on the other side of the wall, we have convection again. Okay, so let's write down what we're given. So we are given a bunch of stuff. So we are given T infinity 1, T infinity 2. We're given H1, H2, L, K, and A. Okay, so all of this stuff here is convection related. And all of this is conduction related. All right, and so we want to find a number of things. So we want to find Q dot, we want to find T1, and we want to find T2. All right, so let's start this process by drawing an equivalent thermal circuit. All right, so we are going to just string this together like how we would. And so we have 3 different thermal resistances in this problem. And we have 4 nodes where we know the temperatures. All right, so I'm just working from left to right. So on the far left, we have our ambient temperature T infinity 1. And then on the far right, we have our ambient temperature 2, T infinity 2. This first resistance that we encounter is the thermal resistance of our convection. As we move through the air, then we get to our left surface of our wall, T1. And as we pass through the wall, we hit conductive resistance. So this is our conductive resistance. And at the other side of the wall, we're at T2. Then we're passing through air again, so we have another convective resistance, RC2, before we get to our ambient temperature at the far side of the second side of the wall. All right, and then in general, we have Q dot going this way. Okay, so what we'd like to do is we would like to write this as an equivalent circuit that looks like this, where we still have T infinity 1 and T infinity 2. And we have our same Q dot going between these two things, and then we have an equivalent resistance. So since we have resistors in series, we can use the rules that we know, hopefully from basic circuits, to write the following. So we have our equivalent resistance is just equal to RC1 plus RK plus RC2. All right, and then we can use this equivalent circuit to say, well, okay, Q dot is then equal to T infinity 1 minus T infinity 2 divided by the equivalent resistance. Okay, and so I can expand this out now. So I can say that Q dot is equal to T infinity 1. Well, let me move this. Okay, so we still have our same numerator, but I'm going to expand out this equivalent resistance. So our equivalent resistance is RC1 plus RK plus RC2. And I'm going to expand those out as well. So I have T infinity 1 minus T infinity 2 divided by RC1 is 1 over H1A plus RK is L over K times A plus RC2 is 1 over H2A. All right, so we have our RC1 is this guy. Our RK is this guy. And then our RC2 is this guy. Okay. So this is how we can find Q dot, given what we were already given to us in the problem. But we also want to find T1 and T2, right? Okay, so we're going to do that by essentially considering different equivalent subcircuits. Okay, so I'm going to draw our picture one more time. So we have T infinity 1, RC1, T1, RK, T2, RC2, and then T infinity 2. Okay, so this is the exact same circuit I drew before. And so, for example, if we wanted to find T2, we would draw an equivalent circuit here. All right, so then we would have T2 on that side and T infinity 1, RC1, T1, RK. All right, and if you remember, we already have our Q dot from before. So our Q dot all across the circuit is the same, so we already have that. This is what we already just found. Okay, and so now our equivalent circuit looks like the following. Where we have T infinity 1 and T2, and this is our equivalent, where our equivalent is our C1 plus our K. Okay, so I can analyze this circuit as the following. So I have Q dot is equal to T infinity 1 minus T2 divided by RC1 plus RK. Okay, and we have everything now, so we can just solve this thing for T2. So we have Q dot times RC1 plus RK. Minus T infinity 1. Or sorry, plus T infinity 1. Okay? We could also do this for to find T2. We would consider this circuit. I'm sorry, we want to find T1 now, right? So if we wanted to find T1, we can look at this circuit. Oops. So to find T1, we would look at this little subcircuit. And again, we're going to use the same Q dot as we had before. So we have Q dot is equal to T infinity 1 minus T1 over RC1. So T1 is T infinity 1 minus RC1 times Q dot. Okay? Okay, if we look back at what our overall equation for Q dot looked like when we considered all three thermal resistances. So if we recall, Q dot is T infinity 1 minus T infinity 2. Divided by the sum of those resistances. So we have our first convective resistance, our conductive resistance, and then our second convective resistance. It looks like this. So if we look at this, what this means is that the largest thermal resistance controls or dominates the rate of heat transfer. Okay. At this point, I know it's a little clunky to ask questions online like this, but are there any questions before I keep going? Okay, I will press on, but interrupt me if you have questions. Okay, so we can use the same idea for even more complicated scenarios. So if we have for example, multi-layer wall systems. Uh, so if we have composite walls, which is just another way of saying a multi-layer wall system. So these types of walls can involve any number of series or parallel thermal resistances due to the layers of different materials. Okay, so for example, if we consider a series composite wall, what we have is we have convection happening on the left-hand side, convection happening on the right-hand side of this wall, but you see that our layers of the wall are sandwiched perpendicular to the direction of the heat transfer. So we'd have Q dot going this way. Okay, and so what we have here is we have this circuit, which is drawn below. So we have our resistance of convection. So this is convection, and then we have convection on the other side too. And then in between, we have conduction through these three different layers of materials that are different. So these are all conduction. But since they're perpendicular, or sorry, the layers are perpendicular to the direction of the heat transfer, so we are considering them as resistance in series. Okay, so if we wanted to make an equivalent circuit, we would have T infinity on side one, a resistor, and then T infinity on side four, where we have Q dot. And then this equivalent thermal resistance is just RC1 plus RK1 plus RK2 plus RK3 plus RC2. 4. Okay. Where we have the following. So we have RC1 is 1 over H1A, and RC4 is 1 over H4A. So these are our convection terms. They show up here and here. And then our conduction terms are RK1, which is L1 over K1A. RK2 is L2 over K2A. And then RK3 is L3 over K3A. All right, and again, these are all conduction. Okay. And then in this type of a system, we can do the same sort of strategy if we wanted to say find T3. So if we wanted to find T3, for example, we would look at this sub-circuit like so. And we would find that Q dot is equal to T infinity 1 minus T3 divided by the three resistors added together as our equivalent resistance. So we have RC1 plus RK1 plus RK2. Oh, okay. Alternately, we could look at the other side of our reactor of our circuit. So we could look at this one. All right, and if we were to do that, we would have Q dot is equal to T3 minus T infinity 4 divided by RK3 plus RC4. Okay? For composite systems, oh, I already have it on the next page. Never mind, I won't write that. Okay, so if we have composite wall systems, it's common to work with an overall heat transfer coefficient, which is called U. And it is defined by an expression that looks very similar to Newton's law of cooling. So we have Q dot is equal to U times A delta T, where this delta T is the overall temperature difference. So for example, we have that Q dot is equal to UA T infinity 1 minus T infinity 4, where we can rewrite this as what we know from before is our equivalent. So if that's our overall circuit that combined all of those resistances before. So this means that U times A is 1 over our equivalent. So we have UA is equal to 1 over the equivalent resistance. Okay. All right. Okay, so we have neglected it so far, but it turns out that the temperature drop across the interface between materials might be appreciable. And this temperature change is attributed to what's known as the thermal contact resistance per unit area. Thermal contact resistance per unit area. And it is defined as RTC. Okay, so if we compare an ideal perfect thermal contact situation, which is what's on the left here, and then an actual thermal contact, which is imperfect, what we see is that for the perfect scenario, the temperature is going continuously through the material at where they are interfaced. Whereas in an imperfect contact, we see that we have these gaps between where the materials interface with each other. So this is realistic because there's really no such thing as a perfectly smooth surface, let alone two of them. And so what this causes is this temperature drop in this little narrow piece of space where our kind of imperfect surfaces are touching one another. Okay, so we would then write this in our equivalent thermal circuit as the following. So we're going to end up with another little thermal resistance that takes into account the interface. So we would have RK1 and RK2. So these are our two conduction resistances for each of those layers. And then we're also going to have our contact resistance. All right, and so here, this is our temperature difference at the interface. And our contact is equal to RTC divided by A. Okay? And then RTC is defined as the temperature drop at that interface divided by Q dot over A. So I'm just solving this equation for Q dot that we would have. And we often call this 1 over this contact heat transfer coefficient. So this HC is called the thermal contact conductance. Okay, and so we could use this with the same circuit analogy that we've been talking about, just like before. And then this contact resistance is going to depend on a number of factors. So it's going to depend on the materials that we use, the surface roughness, as you might expect, surface finishes, fluid filling the gaps, and contact pressure.